So up next we have Mike Ruhanami from Virginia Tech. He'll be joining us virtually. So Mike, if you could share your screen.
Well, hello everybody, and I'm heard, right? Clearly? Okay. The presenter for this ought to be Dr. Shibaji Chakraborty, but unfortunately fortunately he's visiting with his family in India, and it's something like 3 or 4 in the morning. So I'm standing in for him here. And Shibaji has done the bulk of this work as a graduate student with us, and now he's continuing it as a postdoctoral fellow. And the other supervisor of the VT SuperDARN group is Dr. Joseph Baker. It's really great following Rachel and Jim on this because we're speaking to somewhat related themes. I had lots of questions and comments for Rachel, but I was fumbling with my setup here. Apologies, I'm on the road and things are a little awkward where I'm positioned at the moment. But Shibaji has also been looking at flare effects in the ionosphere, specifically at blackouts. Now, this has been introduced very well by Rachel. Of course, what we're looking at here are effects from the sun that are sourced in the sun and the active sun. When you see the sun in visual wavelengths, it's usually quite featureless except for sunspots. But if you look at it in X-ray and EUV frequencies, it's very modeled and variable and active and actually quite exciting, as you can see from this picture. And occasionally you get these explosions from the surface of the sun that we call flares, and sometimes they're directed towards the Earth and they have dramatic effects on the ionosphere, as Rachel described. So Shibaji has set this up in a very sensible fashion. I'll introduce the concept of the flare and its impact on radio waves, and briefly note SuperDARN, which has been discussed in previous HamSCI meetings, so I won't go into great detail on that, and then go into the work that he did characterizing the impact of flares on radar observations, and then conclude with an illustration of how the SuperDARN radars, originally conceived to do other things, can actually be applied to this task of monitoring the impact of solar flares in the ionosphere. So this schematic Shibaji's put together to illustrate the basic concept of what's happening in the ionosphere. The sun is depicted as that, can you see my cursor when I move it around on the screen? Could somebody acknowledge they see my cursor or not?
Yes. Yeah.
Okay, great. The sun, of course, during daylight conditions is the primary factor creating the ionosphere. The EM radiation generates layers of ionosphere we know as the D, E, and F region. The D region has been the main topic here, I think, in the last couple of presentations, and it is in this one as well. It is collisional, which means it's a lossy layer of the ionosphere to EM waves at HF frequencies and below. And the appearance and disappearance of this lossy layer at sunrise and then at sunset is impacting propagation conditions quite dramatically, as Jim described. And another sense in which it impacts propagation conditions is when the sun is active. When there's a blast of X-rays from the sun, the D region, it's very penetrating. The D region is greatly enhanced, and you get a pickup in absorption in the D region that is going to wipe out what has the potential to wipe out your propagation, wipe out your signal before it reaches the higher layers where it would experience the refraction to be redirected towards the ground to create the potential for an amateur radio contact. Okay. There's several terms here. The one I'm going to focus on is the shortwave fade out. That's the primary target of this research. We're looking at that in the lower HF range with our radars from about 10 to 20 megahertz. I guess that's more like the middling part of the HF range. If we have a sudden enhancement of EM radiation, we're expecting the ionosphere to suddenly undergo a sudden intensification, and the impacts in the D region are going to be felt by HF radio systems and AM radio as well, as Jim was explaining. Why study solar flare effects? Well, they're fascinating for one thing. The fact that the sun is stormy and turbulent and causing these disturbances at Earth is fascinating and alarming at the same time. Everybody using HF is impacted by this. Certainly amateur radio, as Rachel showed and Nathaniel has published. It even impacts us in a kind of narrow technical way. We've been at the radars, our radars, working on them, making repairs, and we suddenly see our screen go blank. And we think we've blown something. You know, the trip has been a total loss. We don't see anything. What happened to the signal? Well, it will be more often than not a shortwave fade out event that strikes and it just basically takes us off the air. There's an operational interest, of course, for all those who are working on HF, but there's also a scientific interest that these are all ways of sensing what's going on in the ionosphere. And we can examine the measurements and get at important physics that's going on in the ionosphere. And Shibaji has been active on both of these fronts. And I'm going to highlight the operational aspect of it, but I'll have one slide that will point to some of the scientific implications of this work. So this rather busy slide will remind you that we're part of the International SuperDARN collaboration. We operate HF radars along with partners in many countries, primarily to study space physics. So we're generating signal or returns in the ionosphere from structures in ionospheric plasma. We measure a Doppler shift. We can relate that to the coupling of the solar wind to the Earth's magnetosphere. That's kind of our primary research topic and what we're most known for doing. However, because we're an HF system, just like everybody who's involved with HamSCI, we experience the full effects of refraction in the ionosphere, including the bending over of rays such that they return to the ground and are capable of establishing a radio contact. So where our ray comes down to the ground, we're not actually communicating with anybody. We are in a sense communicating with the ground because the ground will backscatter some of that signal back to us and convey some information about the propagation path and even about the nature of the terrestrial surface where the backscatter is generated. So in our radar scans, we see something that looks like this smallish figure here in the middle of the slide. This is from a radar in Central Virginia, several hours from Virginia Tech. The colored scatter that's seen at further ranges, that's a significant Doppler shift. That's a significant Doppler shift in the backscatter indicating motion of ionospheric plasma. So that's our primary scientific research target. The grayish scatter is due to this ground propagation mode that I described previously. If you had a receiver over this area of northern Michigan and southern Ontario, we'd have the potential for a contact. Now that signal is perturbed by a number of things that happen in the ionosphere, including things like traveling ionospheric disturbances and ULF pulsations and other neat things. And it actually is a medium for us to make scientifically useful measurements. And of course, it's going to be strongly impacted by propagation conditions in the lower ionosphere. So here's a series of scans that give the idea of what it looks like when one of these events occur. The first scan is from 2200 UT. This is daytime conditions. We get this ground scatter band forming. The ionosphere is fairly stable through the day. It sits there. It extends over a certain area of North America on these maps. We have edges due to propagation conditions in range and then due to azimuthal coverage in the other dimension. And we'll basically see that gray band all day long, maybe with perturbations due to TIDs and things. But on this particular day, at 2208 UT, something really radical, dramatic is happening. For one thing, the scatter is somewhat going away. The other part that's really odd and jumps out at you is that now it's colored with a significant velocity. It has a color shading that indicates that apparently has a significant velocity. A little while later, our screen goes blank. That's the point at which we think we've broken our equipment. And then sometime later, it starts to recover. We get a bit of skip distance focusing scatter coming back. And you can see that the sign of the velocity here has flipped from what it was in the initial phase of the event. So this was a positive velocity. This is a negative velocity. So that's the appearance of a shortwave fade out event following a flare in an individual radar in a series of spatial scans. Now we can also look at this in the time dimension. So this covers a period of 2 hours. Now we're just looking on one beam of the radar. So if you like, can think of sitting, looking just constantly in one direction, seeing a fairly stable ground scatter feature up to 1,500, 2,000 kilometer type slant range. And then there's the wipeout. There's the interruption in our backscatter activity, and then a recovery. And you can see how certain features, you can see it's sort of by, you can see by eye how that is coming back. And that's in the backscatter power map. Now, if I look at the lower panel, I'm looking at velocity, where we have gray coding for ground scatter, meaning virtually zero velocity and narrow spectral width. The early part of this event, before the scatter disappears, we see what we call the Doppler flash. We see something that looks like a significant velocity sort of pop up in the remaining scatter. And that, in fact, is the first effect of the shortwave fade out in our observations. When we break these things down to seconds time resolution, we can actually pick that out to a very fine extent. Now, Shibaji's done, there's many details to this, and I'll just highlight the main features, but he's done a full characterization of this because the nature of the observations are quite consistent from event to event and from radar to radar. Now, as Rachel showed, the upper panel here is depicting GOES X-ray flux. So this is a geostationary satellite positioned over North America that will tell us what the situation is in terms of X-ray fluxes. And there's a big pickup here indicating the arrival of a solar flare. The average power in our backscatter observations suddenly decreases. And then, of course, we don't have any measurements, and so we don't have any measure of average power. We can also count the number of ground scatter echoes, which is quite variable with beam numbers. So there's a big spread here, but all that is dominated by the solar flare effect when it kicks on. And then on the bottom panel, one sees this remarkable Doppler flash feature. So the ground scatter had virtually no velocity to begin with, and we saw this dramatic spike reaching an apparent Doppler velocity of 100 meters per second, just about in the vicinity of that, before it dropped and we lost the scatter. Now, Shibaji has characterized this by stages. He has ways of identifying the onset of the HF absorption and algorithm he's developed, also the start of the radio blackout, the beginning of the recovery, and then what you would call recovery. There's sort of a long time frame for full recovery, but there's a period over which you would say, right, the primary impacts on HF propagation have been completed. And so Shibaji has applied that to look at various effects of the SWF in the radar observations. And one of these is the dependence on solar zenith angle. This is one of the questions that Rachel had for her students that she described in her presentation. I think she talked about time of day. Solar zenith angle is related to that. How high is the sun in the sky? This is a day side effect because it's the day side of the Earth that's exposed to the solar flare. And so looking over these three radars, which are spread from east to west across North America at pretty much the same latitude, one can see varying impact of the solar flare on the ground scatter observations of these three radars. And in fact, this particular event was centered more on the western part of the continent. And so you have a deeper and longer lasting blackout effect in the observations. Another question that Rachel posed to her students was the frequency dependence. And this example is conveying the sense of how much the SWF effect is dependent on frequency. And this is not a big surprise because of a very high frequency dependence of absorption through the ionospheric D region. The BKS radar, that's the Blackstone radar in Virginia, operated in this period at 14.8 megahertz, while a radar located in Canada and Northern Ontario operated at a considerably lower frequency. The two radars are about the same zenith angle, so you eliminate that effect largely. And one observes that there's a much more severe effect at lower frequencies. Now on to sort of the operational aspect of this. We have individual radars. Wouldn't it be neat to pull together the observations from all the radars and monitor the conditions of HF propagation in real time or near real time and be able to specify, what's going on with SWF. And so this is a simulation of an event happening in the North American sector. You can see the terminator here separating daytime from nighttime conditions. Some of these radars were not operational, they're colored yellow. Those that were operating, seeing normal ground scatter, have their smallish fields of view colored green. Now these fields of view are quite a bit smaller than the nominal ones for ionospheric scatter because we're primarily sensing conditions in the D region in the vicinity of the radars. The first passage through the D region, although there is a subsequent passage through the D region in order to complete the full ground scatter propagation mode. Now let's see if this is going to run. I'll click this. Yes, the terminator is moving. One can see green largely here. Now red comes on. That's the onset phase. It's over very quickly. That's where the Doppler flash is occurring. And now we're going into blackout, and fields of view are being colored black, indicating that essentially there isn't any possibility of signal detection. And this is happening over a several hour period. But most of the excitement is happening kind of earlier on. Let's see if I can go back to it and run it again. The onset of the event is very sudden, and there is some dramatic physics happening, resulting in that Doppler flash feature and peaking, culminating in the strongest events in X-ray, X-class flare events in wipeout of the HF propagation. And this is a operational tool that Shibaji is working on based on accessing the radars and having real-time links. Now, I said I would mention some of the scientific application of this. Shibaji has taken this another step and has actually modeled shortwave fade out in the ionosphere. The most precise comparisons are with the results of rheometer measurements. Rheometer is another type of instrument that's capable of measuring absorption in the ionosphere kind of overhead. And so it makes a simple one-dimensional type measurement of the anomalous absorption that's associated with something like a shortwave fade out event. So this particular plot in the fuzzy dots that you see is showing the onset of a shortwave fade out event, the absorption rising to 2.5 dB, and then gradually recovering over a more extended period. The existing model, the standard model for applying to this sort of activity and making predictions is called the DRAP model. There's another version, DRAP 2. Shibaji has obtained the predictions of that model. Now Shibaji's gone and derived his own version of a D region ionosphere using different combinations of collision profiles and dispersion frequencies. This is getting into the physics of how EM waves propagate within the environment of the lossy layer of the ionosphere. And so the other colors depicted here are for various combinations of input parameters to the modeling, collision frequencies and dispersion models. And one can see that he's gotten quite good, or it works quite well for predicting the rise and peak of this particular event. And for a short period afterward, the recovery although there's some disagreement as you go further in time. There must be some sort of effect that's not being fully accounted for in this modeling effort. So this is a really great example of a study that has both operational value and interest and is scientifically informative. And there's a point there that, yes.
Yeah, your time is up, so if you could wrap it up, that'd be great.
Okay, I am at my summary plot here. So just to conclude, what we're seeing with our daytime ground scatter simulates ground-to-ground communications, the contacts that we've been talking about, and is susceptible to solar flares. Shivaji has characterized this rather completely and developed a model to account for some of the effects that are seen. And now the big push is on to develop a operational system that will ingest data from the radars and describe solar flare conditions in the ionosphere in near real time. So with that, thank you.